Hello and welcome to this third video in the series, and in this video I'll be explaining the software that drives the turret aimer. And as you can see, I'm using Thonny, which is kind of the default IDE used for programming Raspberry Pis. It's installed by default on the main Raspberry Pi, and it can very easily connect to the Raspberry Pi Pico. As you can see, there are 658 lines of code, and I've split my code into various different functions, and all of those functions are called here in the main loop. So I'll go through the main logic loop first. You can see I have separated these functions with these long lines. So first, the most important thing at the start of every loop is to see whether or not you're in manual mode. And manual mode is in pin 16, and you can see a list of what every pin does up here at the top. Pin 0, pin 1, all the way to pin 16 and the analog read pin. You can find a pinout of the Pico online. You can see here's an example. I just searched Pico pinout and filtered by large. So for example, pin 16 would be over here, and that's where the manual mode switch is connected to. But all of that is covered in much greater detail in the hardware video, which you're going to find up here in the top right corner. So now back to the code and the main logic loop. Of course, the first thing is to read the actual value of the switch. And after you read the value of the switch, you can choose to either do all the instructions and tasks that are required for the manual mode, or if it's set to automatic mode, do all the tasks that are needed for automatic mode. So I'll go through the automatic mode first, since that's the one I actually coded first and it's the more complicated one. But then both of them essentially read the inputs here and here. Then they display what they read on the input OLED here and here. And then they do their own calculations. This one calculates how fast to move based on the position of the joystick. And this is where all the projectile motion is calculated. And then lastly, they display the values that they calculate on the output OLED. But then of course they also have to set the servos in the actual turret to move, so this is done with this function, and it's compatible with both modes, so only one function is needed. But before I get into the specifics of the code, there are a few things. These are all the libraries that I use. This is needed to address any pin in the Raspberry Pi Pico. This is used for timing. This is used to talk with the OLEDs, and this is used for maths. One of the most important functions, which is used throughout the entire code, is this one that I called mapValue. It functions identically to the map function in Arduino in C++, and I've also added this extra feature called cutoff. So to explain specifically what this function does, I'll get a piece of paper. What this mapValue function essentially does is it takes a number between a certain range on the number line and transfers it to another range within the number line, keeping the position within that range constant. So for example, if the initial range is from 0 to 50, with the lower value being 0 and the upper value being 50, and you want to transfer that value to a range between 30 and 60, then you use the function and input these four numbers to set the initial and final ranges. For example, let's say the number you want to map is 25, which is right in the middle of the original range. That means, since it's in the middle of the original range, it will also go to the middle of the final range, becoming 45. Meaning if you input 25 into the function, 45 will be the output. Now what if you want to input something that's closer to one extreme of the input range? Well, let's say you input 10. That means 10 is 1/5 of the entire range. And similarly, the output should be 1/5 along this range. In order to calculate where that is, you need to first find out how big is the range. Well, 60 minus 30 is just 30, and 1/5 of that is just 6, meaning the final output should be 6 above the lower part of the range. So you get 30 plus 6 becomes 36, and 36, which is roughly here, will become the output. So you can think this function converts 10 to 36, converts 25 to 45. If you input 0, it will become 30. If you input 50, it will become 60. This function will still work even if the input is out of the initial range. Let's say you have 100 as the initial input. Well, then you can see the input value is 100% of the input range above the upper value. Remember, this function is all about proportion along the range rather than any set specific value. So you need to go 1 times the size of the range above the upper value. Since this range has a width of 30, you go 30 above that, and this would become 90. So 100 would become 90. That is unless you input the cutoff boolean to be true, in which case the function will cut off any value that's outside of the range. Anything inside the range will also be mapped to inside of the range. So you could check before you even do anything, or you could check afterwards. In my function, I check at the end. So in this case, if it's lower than 30, or if the result is larger than 60, then you just set it to the maximum or the minimum, rather than having that value which is outside the range. So if you understand the task that this function is actually doing, then each individual line of code and the different variables are quite intuitive by themselves. The same with this section on the cutoff, it's also quite intuitive if you understand what the task is. So now on to the part where you read the 6 inputs that are required for the turret to automatically calculate where to aim. And you can see over here I've initialized the values of these 6 values that are needed. So you need the projectile speed of the gun. You need to know how fast the enemy is traveling. You need to know how far away they are initially. Ignore the final. That final here means after all the corrections in code. It doesn't mean at the point of impact. You also need to know the initial enemy bearing at the time of firing. You need to know which direction the enemy is traveling in. And you also need to know the strength of gravity. There are also a few other things that I've done. I've initialized the pins for the 2 dial switches, which set the multipliers for the speed and the distance values. And I've also initialized the pins that are required to actually perform the analog read. This array is containing the 3 pin objects, which are the 3 pins required to set the binary value to the 74HC4051 chip for it to select the correct input to give back. And it's easier to set it in the form of an array rather than having to individually set the value of all 3 pins every time it needs to be done. So now you can see here, these are the 6 values that I've initialized, and I've set them as global variables to be used in this function. I've heard many people say that global variables are bad, you shouldn't use them, but I don't really see a reason why I shouldn't be using global variables in this case. I would think it's much more complicated to have to pass in all 6 values. I've also set the speed magnitude and distance magnitude to global, just so that you can access the values which have been initialized over here. So now these are the 8 analog input pins, well, not input pins, but inputs which can be read, numbered from 0 to 7. So that it can be addressed with just a 3-bit binary value. The first 6, labeled 0 to 5, are the ones required for automatic calculation, and the last 2 are the 2 axes of the joystick used in the manual calculation. So these 2 aren't actually accessed at all in this function. They're used in the manual section. Let me first go through the main sequence of tasks that are performed by this function every time it's called, every time during the loop. First, it reads the values of the 2 dial switches and sets the magnitude appropriately. And after setting the magnitudes, you then loop 6 times, once for each input. So during every loop, you set the appropriate binary value to the 74HC4051, and then given which loop you are on, you then read the inputs and do the appropriate corrections. So now I'll go through the details of each one of these 3 tasks. Firstly is setting the appropriate magnitudes, the appropriate multiplier But before that, what is this speed magnitude variable? What is this distance magnitude variable? Well, it's a variable that gets multiplied onto the value that is read from the various potentiometers that the user sets. It's a multiplier that gets applied to that value. As you can see, for the speed, it can be 0.01, 1, or 100. For the distance, it can be 1, 100, or 10,000. What this allows you to do is to have various different orders of magnitude. If you want to pretend to be a proper naval gun, which fires shells at thousands of meters per second, then you can set the multiplier to 100. With a multiplier of 100, the final value can then range between 100 meters per second, or 100 times that, 10 kilometers per second. This is because all the speed and distance inputs have all been corrected to be between 0 and 100 from their original value between 0 and 65535. This means that this variable here is always between 0 and 100, and the way to set them to any order of magnitude is to multiply them by the multiplier. This multiplier is set by the user using a dial switch, which has one pin connected to 3.3 volts, and the other 3 pins are connected to the Raspberry Pi Pico. Depending on the position of the dial, any one of those 3 pins can then be connected to 3.3 volts, and the Pico is able to read that to see which multiplier the user has set. On the stainless steel top panel, the respective ranges have also been laser engraved. So since a multiplier of 1 allows the user to range between 1 meter and 100 meters, on the panel is the writing 100 meters at this setting of the dial switch. And you can see over here, if none of the 3 input pins are a 1, that probably means that the switch is in transition. So by passing, you just reuse the previous value, and nothing weird will happen if the switch happens to be on transition. So now onto the part where you set the binary output for the 74HC4051 chip. I'll now again get some pen and paper and explain it that way. To understand this section of code, first it's important to understand this 74HC4051 chip that I'm using to be able to interface with 8 analog inputs at the same time. These 8 analog inputs come from the 6 potentiometers on the control panel, as well as the 2 axes of the joystick, and they are connected to the 8 input pins of the chip. They're numbered Y0 to Y7, which is what the datasheet calls it. In order to select which one of these 8 pins is connected to the output pin, which is called Z, a 3-bit binary value is needed, since a 3-bit binary value is able to represent all numbers between 0 and 7. So this side is connected to the control panel, and this side is connected to the Raspberry Pi Pico. What the Pico needs to do is set this binary value to the one that it wants to read out of the 8, and then the chip is able to do its magic and output the analog voltage on this pin so that the Raspberry Pi Pico can read it. What this chip essentially does is saves a lot of analog pins, because the Raspberry Pi Pico is now able to interface with 8 analog pins while only needing to use up one of its own analog pins. And since there are much more digital pins compared to analog pins, this is a very useful chip in this case. For example, if you want to access the voltage on Y6, which I believe is connected to the x-axis of the joystick, what you have to do is set this binary value to 6, being 110, and once it does that, the chip sees that it's being asked to connect input number 6 to the output. So it does that, and now whatever voltage is on input number 6 is outputted on the output pin. The same thing happens for any other input that you choose. If instead of 6 you choose the input 0, then it connects the 0th input to the output, and you can then read whatever potentiometer is connected to this pin. What the Raspberry Pi Pico has to do then is to set the 3 binary pins to the binary value of 0, and then read the analog input, and then set it to 1 and read it, set it to 2 and read it, all the way on until it sets it to 5 and reads it. That means it's read the 6 inputs and it's stored them as values which are then usable in the calculation. To understand how the Raspberry Pi Pico sets these binary outputs then, it's important to understand the variables and arrays that goes into doing this. First, there's an array called analog selection pins, which stores the pin objects of the 3 pins in increasing significance. So the pin that's connected to S0 is stored in the 0th position of the array, S1 is in the first position, and S2 is in the 2nd position. Meaning, if you put in analog selection pins square brackets 1, close square brackets, then it's referencing the digital pin that's connected to S1 of the chip. Next is this array that I generate called bitmask, which is useful for actually setting the binary output. Its values are integers, but it's more helpful to view them as binary numbers. They are stored in the order of 1, 2, and 4, and since these are the values that each binary digit represents, it becomes useful later. Next, this analog input variable is the counter used when referencing all 6 inputs. So this ranges between 0 and 5 and references the inputs 0 to 5 which need to be read. And written out in binary, it's like this. And lastly, this pin counter, it's used in a for loop for every single one of the 6 inputs. It references the 3 separate pins here, and it ranges between 0 and 2, so 0, 1, and 2. So the line of code that actually does all the work is this line. Analog selection pins with the index of pin should have a value of analog input and bitmask with the index of pin. To better understand how this line works, let's give some examples to the values of these variables. Let's say you're trying to reference analog input number 3, which is actually the 4th input, just labeled 3. And you're trying to set the 1's pin of that. So pin in this case would be 1. What this automatically does is, since this array stores the pin objects of the 3 pins, by putting in 1 as the index, you're referencing the pin that's connected to this pin. So you're setting the value of that pin, which is what you want. And the value that you actually set it to, well, it's either a 0 or 1, it's either low or high. But actually in MicroPython, inputting a value of 0 over here turns the pin off, but inputting any other value turns it on. So inputting 1 will set the pin high, inputting 2 will set the pin high, inputting 0.01 will also set it high. So it doesn't matter what's inside this bracket, as long as it's not a 0, the pin will be set to high. So written another way, the analog input that you're referencing is 0, 1, 1, and the value of the bitmask array at index position 1 is 0, 1, 0. And by ANDing them, you're essentially finding out whether or not the value at the 2's digit of this number in binary representation is a 1. Let's say instead of being a 3, this value was actually 1. So the binary representation will be 0, 0, 1. And when you're ANDing multiple digit binary values, each value gets ANDed separately. So 0, 0, 1 ANDed with 0, 1, 0 is some other 3-bit binary number. You can see immediately the purpose of the bitmask is that any digit that's not the digit you're trying to reference immediately becomes a 0. Because only the digit that matters is set to a 1, and anything ANDed with a 0 becomes a 0. So these automatically become a 0. The remaining digit then is whatever the value of this number at this digit is. And this number, remember, is the analog input you're trying to reference. it's which one of these 6 you're trying to reference. And in this case, when it's a 1, the 2's digit is a 0. This turns out to be a 0, and you're inputting 0 to the value of this pin, which means that this pin should be turned off in order for the number 1 input to be referenced. However, if like originally this wasn't a 1 and it was a 3, the binary would be 0, 1, 1. And doing the same thing again, 0, 1, 1 ended with 0, 1, 0. Again, the zeros make these digits completely useless immediately. And all that matters is the remaining digit, which in this case is a 1. So 1 ended with a 1 becomes a 1. And in this case, the number is no longer a 0. Even though it's actually a 2, as long as it's not a 0, which would only happen if the selected digit is a 1 and not a 0, then the pin will turn on. Meaning this pin here will become a 1 as soon as this line is executed. Remember, this line of code is executed for each one of these 3 pins to set its value for each one of the 5 inputs. So every time throughout the main loop, this piece of code is executed 18 times. So if you're trying to set the value of the 0th pin, which represents a binary value of 1, the pin in this case will become a 0, and the bit mask will be 0, 0, 1. You're still trying to reference input number 3, which is 0, 1, 1. As before, these 2 zeros make these useless, so these immediately become a 0. But this remaining 1 means that the 1's position of the binary value should be a 1. That gets set to a 1, which is not a 0, causing the Raspberry Pi Pico to set this pin to a 1. And similarly, when the bit mask is 1, 0, 0, this digit is referenced. This digit has a 0 over here, so all of these will be zeros, causes the Pico to set this to a 0. And what this has done is set the binary value of 3 over here, which causes the chip to connect the 3rd value over to the common output, and the Raspberry Pi Pico is then able to read that and interpret that value. So here's another way of thinking about this scenario in terms of the 4 pins that are interfacing between the SEM4HC451 and the Raspberry Pi Pico, and how their voltage varies over time. This is a bit like the screen of an oscilloscope. So across here is time, and up and down is voltage. These are just 4 separate lines. So these columns are indicating which analog inputs the Raspberry Pi Pico is trying to retrieve. These 3 are the 3 binary pins, and this one is the analog output that's actually being read. You can see when it's trying to reference pin number 0 or 3 or 0. When it's trying to reference pin number 1, it's 0, 0, 1. When it's trying to reference pin number 2, it's 0, 1, 0, and so on and so on. After the appropriate voltage is set, the returning analog voltage can be read. Here I just made them up randomly, but the height of this line, which represents the voltage, indicates what the user's input actually is. Once the correct binary output value has been set, you can then move on to reading the actual return from the SEM4HC451 chip. And the common pin is this pin, analog read pin, which is pin 26. Within each one of these 6 sections, which are called depending on which one of the inputs are being read, a few things happen, and it's similar across all of the different inputs. First, you read the analog read pin, which returns a value between 0 and 65535. It's a 16-bit binary value. However, there's a bit of error in the hardware. When the potentiometer gets set to 0 volts, it doesn't actually register as a 0. It fluctuates between about 300 or 400. So I use the map function here to map between the value of 500 and the maximum. This means that any value below 500 will get cut off and will automatically be set to a 0. And this means that when the user sets the potentiometer all the way to the lower extreme, a 0 is actually registered. So this variable stores the input value as a number between 0 and 65535. But as I've said, I want to convert it to a number between 0 and 100. This is also because of the precision of the analog read. Even if the voltage is exactly the same, the Pico reads it as a number that's maybe 100 or 200 off in the 16-bit number every time, even if you don't change anything. So by rounding it to the closest number between 0 and 100, you can make it fluctuate less and make it stick to a certain value more. I'm rounding to 0 decimal places, which is essentially rounding to the closest integer, and this allows it to become an integer between 0 and 100. And lastly, the final value of the input, which then gets used in the rest of the code, is just this previous map value multiplied by the magnitude multiplier, which has been set by the dial switches. This same process is repeated for all 6 input pins, and since the outputs are global variables, I don't have to return anything, and that's the end of the function. Now that the 6 input values have been read, the next job for the Pico to do is to display them on the OLED display that displays the 6 inputs. For this, I use the I2C bus 0, which is using pin 0 and 1 on the Raspberry Pi Pico, and I've just set it to the highest frequency that I find works. This OLED object is set up using the SSD1306 library, which I've imported at the top. The SSD1306 is a chip that's used on the OLED display module itself, and using this library you're able to communicate with that chip and display information on the display. This OLED object makes use of the I2C object that's been set up in the previous line. So with the Raspberry Pi Pico, the only setup that's required for an OLED display are these 2 lines. So now onto the actual function itself. You can see these 6 variables, which are the final values that's been read from the previous input function, are again used as global variables. And in comparison, this function is so much more simple compared to the previous one. It's just a few lines. First, I clear the OLED by filling it with the value 0, and then I essentially output the 6 values one by one. For each of these, I use an abbreviation. For example, projectile speed, I use it as V, and this is supposed to be a subscript, so it's like V sub P. And for each of them, I round the value to 2 decimal places, otherwise it could take up too much space on the OLED and overflow the line. I then add the appropriate unit onto the end of the line, and these 2 numbers here set the position of the value to be printed. All of them start on the very left, which is why they start at 0, and each one is 10 pixels down. There are 64 pixels vertically, so 6 values, each of which are 10 pixels high, fit quite nicely onto the OLED. With the OLED on the Raspberry Pi Pico, each of these values send the appropriate string to the module, but they don't actually get shown. They are only stored in the module. They only get shown when you tell it to show with this show method. Now that the input values have been displayed on the OLED, the processor moves on to actually calculating the 2 outputs. How high to aim the gun, which is called elevation, and how far around to turn the gun, which is called train. This is the core part of the entire project, which is to do the automatic calculation, to do the projectile motion calculation, and most of it is handled in this function called calculateTargetAnglesAutomatically. Before that, here are a few variables that are used. This out of range variable is a boolean to indicate whether or not the shot is achievable with the current settings. And these values here are the outputs, which are calculated by the function. In theory, only these 2 are actually needed, but I display the rest of these anyway, since they are very easily calculated and they are interesting information to see. So as before, I initialize these values and set them as global variables, so the function knows to use these values. But I've actually written this function before doing the entire code by itself, and there I used different names for the variables. So to save myself the effort of having to go through to change the name of every single variable, I just set them to the appropriate values. This is the function within the function that actually performs the numerical trial and error to solve for the elevation of the gun. And again, I'll be using some pen and paper to explain how exactly this works. So what is this section of the code doing? Well, this section of code is solving an equation with a certain unknown that's very difficult to rearrange and solve traditionally. Something like this. For example, x squared minus 6x minus 20 equals 1/3 sine squared for x, sine being in radians. Now I do know the answer to this equation. It's either negative 2.38 something something or positive 8.40. How do I know this? Did I rearrange the equation and solve it? No, I didn't. I typed it into Wolfram Alpha. But unfortunately, Wolfram Alpha is not supported locally by every Raspberry Pi Pico. What I have to do is write my own function to imitate what Wolfram Alpha is doing, which I'm pretty sure is essentially trial and error and seeing which values are the closest. And how do I do this? Well, let's just assume you know that one value is roughly around 8. I'm just ignoring the negative one for now, just caring about the positive one. In the actual turret, I know the final result should be an angle between 0 and 45, so that's what I start my range for testing as. In this case, I'll set it as between 6 and 10, and I'm trying to find this value where the left-hand side equals the right-hand side given the value of x, and x can, I'm just arbitrarily choosing, x can range between 6 and 10. So what do I do now? Well, I try different values between 6 and 10, and I've just chosen to go up by integers right now. And to do that, you need to know three things. You need to know the value of the left-hand side of the equation, which is this. You need to know the value of the right-hand side. I need to know the absolute value of the difference between them, because that's how you compare. The differences can either be positive or negative, but what you want is for the difference between the two sides to be 0, since if the difference is 0, that means the two sides are equal, and that's what you want in an equation. So here's the absolute value of the difference, and I've tried them out for all 5 values over here. You can see the closest one is 8 with a difference of 4.1013 between the left-hand side of the equation and the right-hand side of the equation. And that makes sense because the actual value is closest to 8. But of course 8 is not very precise. You want to go to more decimal places than just 8. So the next step is to narrow down the range and try smaller values. So how much can you narrow down the range but still make sure that the actual solution is still within the new range that you've set? Well, you know that 7 has a value that's larger than 8, and 9 has a value that's larger than 8. So you know the true value must fall somewhere between 7 and 9. Assuming, of course, there is a true value. There are some equations with no solutions, but you are assuming there is a 0, and you're assuming that the 0 is closest to the smallest value right here, which in this case it is. So the new range should be set to between 7 and 9. You can see that within this first attempt, which I'm calling a level, within this first level, I'm trying 5 different values with a difference of 1. Well, when I narrow down the range, I still want to keep trying 5 different values so that I can actually increase the precision. If I still just try integers, then there's no point in narrowing down the range. So I still try 5 different values. So now you can see I've made calculations for the new range between 7 and 9. Again, I have 5 values within the range, this time every 0.5 rather than every 1. And instead of listing out the left-hand side and the right-hand side separately, I've just gone ahead and directly calculated the absolute value of the difference between the left-hand side and the right-hand side. And since we know the real value is 8.4, it makes sense that 8.5 has the smallest difference between the left and the right. And this means that in this level down, 8.5 is the closest value, and the next level down should have 8.5 in its center, and have the upper and lower range be 8 and 9. And now I've included the next level down, the range between 8 and 9, split into 5 different values. You can see that, again, 8.5 is the closest to being 0, but 8.25 is actually quite close as well, and 8.75 is further away. So if I were to go down another level, I would set 8.25 to be my lower range, 8.75 to be the upper part of my range, and then try 5 values within there. Actually, there's no reason why there should only be 5 values per range. In the actual code, why I do the trial and error with this method, I have 20 values per level, so actually 4 times more than this, and I have 3 levels in total. So now that you know the theory, let's have a look at how it works in the code itself. This part calculates the left-hand side of the equation, which I figured out by doing the maths, and you can see my explanation of the maths of this project up here in the top right corner. And then this function is what you do to calculate the right-hand side of the equation. X here being the elevation of the gun, since that's what the most difficult thing to find is first. And once you know the elevation of the gun, everything else is very simple to find. And now you initialize the range within which the function will try values and see which one's the most optimal. I've just set them to the minimum solution value and maximum solution value, which is what's been inputted every time the function is called, lower down in the main loop. And now that you've set the minimum and maximum values, you have to loop through the number of times there are levels. And for every level, the processor generates this array called values to try. These are the various values within that level that the processor tries and performs the calculation on to see which one is the most optimal. The range size, of course, is the difference between the upper part of the range and the lower part of the range. And the increment size between each value to try will be the range size divided by this. The increment size is what you add to get from one value to the next. So you need to divide by the number of increments, which is 1 less than the number of values. Now to actually generate the values in the array values to try, you loop through an amount of times which is the same as there are values in the level. And for each one, you start at the lowest part of the range and you add on I times the increment size, I being of course the counter in the loop. I round this to 5 decimal places to avoid floating point errors, and this is something that I added in while I was still experimenting with this part of the code so that the debugging information that I was printing was more readable. So now that you know which values between the range you have to try, you then generate this array called differences, which is essentially the result for each value. The difference being, of course, the difference between the left-hand side and the right-hand side, since that's what you're trying to minimize in order for the two sides of the equation to equal each other. Now, for each value in the array, values to try, the left-hand side of the equation is just calculated by the function that's been set above. The right-hand side is calculated similarly, and the difference is just the absolute value between the left and the right. So then, once you've done this part of the calculation, you just append it to the differences array, and now you have 2 arrays. One is the various values in degrees that you're trying, and the other is the difference between the left-hand side and the right-hand side, which is the result. And since they line up perfectly, because there are an equal number of them, you can access both of them essentially with the same index. This means that if you find the value with the minimum difference over here, just with the min function, you can then find the index position in the differences array using the index function. And given the index of the value with the minimum difference, you can then retrieve the actual value in the array of values to try using that index. And that gives you the closest value in this level, which in this case is in degrees, to actually having the two sides of the equation equal, meaning having the smallest difference. And the next part is narrowing down the range for the next level down. These two are special cases, so don't worry about them for now. Most of the time, these two lines are executed. Remember, this variable stores the index position of the minimum value, and to set the range for the next level, one extreme of the range is just the value that is one index lower than the previous, and the other extreme is the value that's one index higher. But of course, if your value happens to be the lowest part of your range already, then you can't get any lower than that, and your range lowers down to between itself and one index higher. Same with if your value is already at the upper extreme. So once this entire section has been looped through for the number of levels there are, then the closest value is then obtained, because that's the value that you get for the very last level, which is the most precise one, and that's returned. This completes the part of the overall function, which calculates the elevation of the gun, and these other functions just use that as an input to calculate the various other numbers that are needed. Again, all of these formulas have been calculated using maths, which is shown in the maths video. But all of what I've shown just now are only functions, and the functions need to be called. The reason I've set them as separate functions is because the code's much more readable if I can just list them out like this. Before that, there's this try and accept part. This is because some parts of the maths you could be maybe dividing by 0, or taking the inverse sign of something that's not between -1 and 1. And in those cases there will be a maths error, and this wouldn't work, so you would go into the accept. And what that almost certainly indicates is that the shot's unachievable with the current settings, which means that the shot's likely out of range. So instead of doing all the calculations, I just set the out of range boolean to be true and go through the loop again. But if there aren't any maths errors, then this is how the rest of the code goes on. I first calculated the elevation of the gun using the function that I talked about. I ranged the possible values between 0 and 45, because even though there could be another solution between 45 and 90, it's the less efficient one if the flight time will be longer, meaning the shot will be less accurate. So I just range it between 0 and 45. And these two values here, meaning I choose to have 3 levels, and for each level I split the range into 20 different values. I found just throughout trial and error that this is the best compromise between precision and speed. With this setting, the processor only takes about 30 milliseconds to perform one entire set of calculations, meaning ideally there can be about 30 updates every second to the calculation. After the elevation of the gun is calculated, all the rest of the interesting values are calculated using their respective functions. And lastly, the other more important thing is the train of the gun, which in this case I've called bearing. I have a very high inconsistency with my variable naming since I did this section of the code first before I established the standard. And that again is calculated using its appropriate function. I then set these to the appropriate global variables, and lastly I implement another check to see whether or not the shot is out of range. I find the difference between the left-hand side and right-hand side, and if their difference is above 0.1, which is 10%, then it probably means that the shot is unachievable. and there just happens not to have been any errors throughout the calculation. And again, since these two are global variables, I don't have to return anything in this function, and that means that's the end of this function. So now that I've calculated all of those output values, I can then display them. This part of the code is very similar to the part where I display the inputs. It's again setting up the OLED, this time the output OLED, and also it's setting up the out of range LED to turn on the LED if the shot is unachievable given the inputs. Like before, I set the variables to be global, I reset the screen, and I output all of these values. This time there are actually 8 values, and very conveniently 8 times 8 equals 64, and there are 64 pixels. So that just means between every row I set them to be a 8 pixel difference, and that fills the OLED perfectly. Lastly, I use the show method to again actually display the values. Before I move on, I want to talk a bit more about the part where I do the actual calculations. All of these angles here are in degrees. You can see there's a lot of conversions using the math library between radians and degrees. This is because while I was initially coding, I had a lot of trouble with having different standards for the different angle variables, and I had to spend hours finding out problems and troubleshooting just to realize that's because I hadn't kept track which variables were in degrees and which variables were in radians. So I decided to just unify a standard, have all of my variables be in degrees, but that means every single time I use them I need to convert them to radians, since the math library's trigonometric functions take radians as inputs. The other thing you can see is that in many of these functions I have multiple lines. This is because, for example, the enemy travel distance is used multiple times in the final calculation. This means that if I calculate it separately first, I'm able to make the calculation more efficient, and I don't have to recalculate these sections of the formula. Now that I've calculated the elevation and terrain that has to be set, I can then output it to the 2 servos, which actually physically move the turret to set them. As far as I could tell, there aren't actually any servo libraries for the Raspberry Pi Pico, so I had to look into the standards of communication with servos, and essentially writing my own library is just a bit of code that makes use of the PWM pins on the Raspberry Pi Pico. The signal pins make use of a PWM signal that has a frequency of 50 Hz, and you vary the angle of the servo by varying the duty cycle of the PWM signal. For my specific servos, which are 360 degree servos, which are different from the normal 9-gram servos that only range between 0 and 180 degrees, the duty cycle that they take in is between 0.025, which is 2.5%, and 0.125, which is 12.5%. I set this appropriate PWM signal, as I said, using a PWM pin on the Raspberry Pi Pico. I initialize the pin and set its frequency to 50, which I don't have to change anywhere else. I then take the 2 calculated values as inputs. I perform various corrections to them, and then I finally use this actuateServo function to actually set the value of the servo. Having a closer look at the actuateServo function, it takes in the PWM pin object that is connected to the servo as one input, and it takes in the desired degree as another input. First, the duty cycle is calculated. This variable ranges between 0 and 1, and since the desired degree is between 0 and 360, since I have a 360 degree servo, I first use the mapValue function to convert it to a value between the appropriate range of duty cycles. And because it's between 0 and 1, I can simply multiply by 65535 to get it to range between 0 and 65535. I can then use this variable and set it as the duty cycle of the servo, which again is the input. And this then changes the actual electrical signal that's outputted on the servo pin. For both the train and the elevation, I first perform corrections to it before telling it to actuate. You can see for the elevation corrected degree, it runs it through this elevation correction function before actually sending it to the actuateServo degree, which uses the elevation servo pin, which is set up here, the PWM pin object as one input, and the corrected degree as another. Even though the entire servo is able to move between 0 and 360 degrees, I'm only using 90 degrees of that range, since the gun barrel only ever move between 0 and 90 degrees. However, the servo isn't mounted perfectly aligned with 0 degrees, which is why I need a correction. I first cut off values that are out of range of 90, even though that should never happen, because no values that are out of range would ever be outputted by the automatically calculating function. But I do it anyway, just in case, so that the servo doesn't move too far and break anything mechanical. I then map this value between 0 and 90 to between 238 and 145. These two seem like arbitrary values, and they are. I found them out using trial and error to see which values actually move it. And you can actually see that the lower value is bigger than the upper value. This means that the servo rotates the opposite direction to the way that I mounted it. And by doing this, I'm able to reverse its direction. Similarly, with the train correction function, with this, since I'm using the entire 360 degree range, there isn't that problem. But again, I have to reverse its direction since bearings are going clockwise and the servo seems to spin by default anti-clockwise. So after the correction, like I said, it gets sent to the actuateServo degree, which then connects through the USB wire to the servos and causes them to move. And that's everything there is to the automatic mode of this turret tamer. You can see this function is called actuateServos, and going all the way down to the main logic loop again, that's the last task performed in every loop in this while true loop. So I've already explained everything over here. Now there's just the manual mode left. First, since there's never any use of the out of range LED in the manual mode, I just set it by default to be off. I then perform these 4 tasks, which are very similar to the 4 tasks in the automatic section. I again read the inputs, I display them, I then perform calculations. I then display the results of these calculations, and then I physically move the servos. The function for reading the joysticks is much simpler compared to reading the 6 inputs. It uses the same theory, where you have to first set an appropriate binary output value, which in this case I just hard-coded in. With just 2 axes to read, there's no point using the entire fancy binary bit mask thing. I just do it simply by setting the output values. Before that, however, let me show you the main thing that this function is actually doing. What this function is essentially doing is converting the left and right movement of the joystick to a value between -1 and 1. So normally the joystick rests in its middle position, which is roughly when read by an analog input pin in the middle here, between 0 and 65535. But of course it doesn't rest perfectly in the middle every time. There's a small bit of difference every time it springs back to the normal, and you don't want that tiny bit of difference causing the turret to move when you don't actually want it. What this means is that there's a range in the middle around where the joystick will spring back to, where the value is accepted to be 0. So this is called the dead zone. And within this zone, any small movement of the joystick wouldn't count. It still counts as 0 and there won't be any movement at all. It's only when you move past this upper limit of the joystick that it starts counting for movement. So you can see, when you're moving only a little bit above the dead zone, let's say over here, then the actual amount of movement will only be quite small, about 0.3 times the maximum speed. If you go all the way to the extreme, which is roughly 65535, it will go all the way to 1, and 1 is the maximum speed. Same with the other direction. If you're only going a little bit below the lower extreme of the dead zone, then you will only move in reverse a little bit, but if you go to the extreme, you will move a lot. Now that you know what the function is doing, let me show you how it's done. First, it reads the x-axis of the joystick, which moves the train of the turret. Since the x-axis is on address number 6, I set the binary output to be 110. I then simply read the analog input, and like before, I apply corrections to it. This time, not only do I cut off lower values, I also invert it, because it seems like I connected it the wrong way around, and it's just easier to invert it in code rather than to physically change the wiring, which would require me to open up the entire thing. So the first check I do is whether or not it falls within the dead zone in the middle. If it's larger than the smallest part of the dead zone, or if it's smaller than the largest part of the dead zone, then that means it is within the dead zone. And this delta train variable is essentially the degrees per second output of this function. If the analog read is within the dead zone, that means I don't want the turret to move at all, so I set the output value of this function to be 0 degrees per second. However, if it's larger than the maximum, then that means I want it to actually move. And how much I want it to move depends on how far the joystick has been pushed. If it has been pushed to extreme, I want it to move a lot. If it's not been pushed a lot, I don't want it to move as fast. That's the whole point of using a joystick rather than just some buttons. I again make use of the mapValue function, this time between the upper part of the dead zone and the very top, which is 65535. And this set maps it to the value between 0 and 1, meaning a value just above the dead zone only has a very small amount of movement, and a value near the extreme of 65535 has a very large amount of movement. This value between 0 and 1 then gets multiplied by the maximum speed, which through experimentation I found was about 200 degrees per second. And that means that this gets translated into the final value in degrees per second that the train servo actually has to move. A similar thing is done if the value is below the minimum point of the dead zone, in this case mapping it between -1 and 0. So the output would be a negative value in degrees per second, and you'll see in a moment that means it subtracts from the angle and causes it to move the other way. This entire process is repeated for the y-axis, which moves the elevation of the turret, so I won't go over it again. And lastly, I just round this degrees per second value to the closest integer. Since the value ranges between 0 and 200, such a small decrease in precision doesn't really matter. So now I've read the joysticks and interpreted their output, meaning I know how fast to move the turret in degrees per second. I display this information using the same input OLED that's already been set up in the automatic section. Like before, I reset it, I output, and then I show it. There's nothing new about this section. It's just like before. Just knowing the speed that the servo has to move isn't enough, however, because the output to the servo is the output in terms of position. So the processor itself needs to know the speed and do calculations with it to set the target position that actually gets sent to the servo to be moved to. And to do this, I have this function called calculateTargetAnglesManual, as opposed to calculateTargetAnglesAutomatic. It takes this delta elevation and delta train as input, which, as I've said, is in degrees per second, and it outputs the position, which, just like the output of the automatic section, is calculateElevation and calculateTrain. Since every iteration through the main loop takes a different amount of time, I need to keep track of the amount of time that has passed since the last change in position, so I know how much I actually have to increase the position in degrees to maintain the set speed. I initialize this time of the last change as 0, and every time I call this function, you can see how many seconds it's been since the last change using the uTime.tixms. This is part of the uTime library, which gives you a value in milliseconds of how long it's been since the code started running. It doesn't actually matter how long the code's been running. All that's needed here is the difference from the last time the function has been executed. And since it's in milliseconds, I divide it by 1000 to find it in seconds. However, say if I start with manual mode, then switch over to automatic mode for a minute, and then switch back to manual mode, that means that it's been a very long time since the last time this last change value has been set. And what that means is that in theory, the turret would have to move a lot to create an average speed of say 200 degrees per second over a minute. So in cases like that, I just don't do anything if the time since the last change is above 0.5 seconds. However, if it's not above 0.5 seconds, that means I've been in manual mode, so then I move on with the main part of the calculation. It's quite confusing because I have these two variables. One's called change in elevation and one's called delta elevation, both of them meaning change. But delta elevation is a speed in degrees per second, and change in elevation is the actual amount of degrees given the time it has been since the last change that I need to make. So the calculated elevation is the position that the turret is physically at right now. And I need to add that change in order to update the physical position. For example, if I want to move the turret 10 degrees per second, and it's been half a second, this will be 10, this will be a half. That means in this half a second, I should have moved the turret by 5 degrees. And then this variable here will be 5 degrees. That gets added on to the final output, and that moves the actual servo 5 degrees, which then creates an average speed of 5 degrees per second. Now, of course, I don't want the value to be out of range. So for the elevation, I don't want it to be under 0 or over 90. For the train, I don't want it to be under 0 or over 360. And the easiest way I found to do that was just to use the cutoff part of the mapValue function. If the calculated elevation is already at 0 degrees, and I try to move it even less than that, this function will prevent that from happening. And lastly, at the end of the code, I update the last change value with the current time, so that the next time this function runs, it knows how long it's been since the last time it's been changed. So now that you know the position that the servos actually have to move to, that's also useful information to be displaying. So I display this information on the output OLED, just again like the previous display parts. But then of course, since the actuateServos function only takes in the two variables of calculateElevation and calculateTrain, it's able to work with both the automatic section and the manual section. So all that has to be done is to set the value of those two variables, and this function automatically physically moves the servos. And that means that's everything in the code. Nothing else is required for the turret to work as it does now. So I hope you've enjoyed this video, and if you want to go into detail on how the hardware of this turret aimer works, or how the maths of this turret aimer works, then you can click the videos on screen now.